So we said the IPCC keeps making projections every 7 years or so now, 2007, 14, and 21. And there are always debates about whether this way of doing things should change and so on. But it's worth looking at how the models improve from one projection to the other. There is enormous amount of work that goes into these, with lots of groups across the world participating. Initially they were dominated by the US and Europe, and now we have models from China, India, Australia, of course, South America, and so on. And the model resolution gets better, process understanding translates to improved complexity and details of the processes in the models, and we saw the evolution history of adding things like sulfate and non-sulfate aerosols, aerosol direct and indirect effects, land ice and ice sheet, and of course other things like dynamic vegetation and so on and so forth. Here is a quick look at a few things. So this is the annual mean surface temperatures. We are looking at correlation coefficients and looking at the observations in green dots and the version from 2007 AR4 report, and the my computer is doing a version from 2014 which is called CMIP5. This is coupled model intercomparison project. Okay, so this is organized, coordinated by the WMO, World Meteorological Organization. As I implied before, generally the skill of representing the surface temperatures is pretty good in the model. So you can see both CMIP3 and CMIP5 have very high correlation with observations, but this is in a global mean sense. One always has to worry about the local changes, and we'll see one little evidence that from CMIP3 to CMIP5 the model's ability to do regional scale changes has also improved marginally. And there are lots of papers. Each time a new set of simulations is released, hundreds of papers are written comparing versions and reporting improvements or lack thereof, and also analyzing how things have changed in terms of ocean warming, land warming, atmosphere warming, extremes, sea level rise, marine ecosystems, corals, acidification, and so on and so forth. So what we call before the emitted terrestrial radiation is the outgoing long wave radiation, which is a very key part of the energy budget, but also shows you how the energy balance is being done with the increasing greenhouse gases, land use change, and so on, urbanization, which is part of land use change, deforestation, and so on. So you can see that CMIP3 was a little bit further away or had a lower correlation compared to observations than the CMIP5. So this is correlation between observations and CMIP. So obviously observation with itself should have green dots show correlation coefficients for alternative observation datasets indicating uncertainties in observations themselves. So observations themselves are fairly agreeing with each other in surface temperature and outgoing long wave radiation, but different observations have some disagreements or uncertainties when it comes to precipitation. As we said, simulating and observing precipitation is a very difficult task because the decorrelation scale of precipitation is very small. It could be raining here and not raining right over there in the same place. Okay, and this is called shortwave cloud radiative forcing. So you look at a region which has clouds and a region which is cloud free, and you compare the differences in shortwave and long-wave radiations, and you create shortwave radiation forcing and long-wave radiation forcing by clouds. This is a very good indicator of how the cloud simulations are being done and how that affects the radiative balance. Clouds are very hard to do as well. They are somewhat harder than precipitation, but precipitation we have lots of data and we can easily see what the models are doing. But with clouds, with especially multiple levels of clouds and multiple categories of clouds, even the data is not that good, so you can see there is some uncertainty in the shortwave cloud radiative forcing there. But nonetheless, precipitation overall has improved compared to observations from CMIP3 to CMIP5, and the improvement in shortwave cloud radiation forcing is a tiny bit, and the range of correlations between models is quite large in CMIP3. That range has been squeezed to a smaller extent, to a closer range in CMIP5, but as far as shortwave cloud radiative forcing is concerned, there is not significant improvement. So this should give you pause in terms of the ability of models to do certain things very well, but other things not so well. So for example, if somebody is looking at monsoon simulations from CMIP5 models for the historic period, that's typically how evaluations are done. You evaluate against observations over the historic period for however long you have data, and then you use that as a guide for understanding the uncertainty of the projections in those models. It's a very difficult job, but nonetheless the science is very good and robust. So if Indian monsoon seasonal cycle is being done very well by a model, then you have to further evaluate it to see whether it is also doing sub-seasonal or intra-seasonal variability, because the critical component intrinsic time scale of the Indian monsoon is that it has these active and break periods. You can look at the monsoon podcasts I have for the details. But if a model is doing a good seasonal amount of rain but not doing the active and break periods, then it may be getting the right amount of rain for the wrong reasons, and so on and so forth. So all kinds of details exist. One has to keep that in mind. Just to extend that a little bit, this is showing observations of temperature and salinity in these dark, in the black contours from the so-called World Ocean Atlas, which is a compendium of data over a long time. And the colors and the white contours are the differences between observations and models. So you can see that typically models do not do the thermocline so well, and they have biases in the deep water formation side, and these differences are not small, right? They are remember I said even a small warming in the ocean amounts to large amount of energy, so you can imagine that these large differences in temperatures correspond to large differences in energy as well. So one has to understand these biases. As I said before, ocean mixing is parameterized because we don't have very good measurements for it. We don't have a very good handle on it. There are lots of details there which I'm not going to get into, but that those kind of things matter, and you can see the biases in salinity as well. Together these result in biases in density and biases in amount of deep water formation, thermohaline circulation, which means heat transport, which means modulation of the global warming, and so on and so forth. So there is this cascade that one has to understand. But again, models are amazing because given just the energy coming in from the sun, they are able to produce all this information at all time scales. even though there are small biases, there is incredible amount of useful and accurate and usable information in these models. So here is a little bit more about total ocean heat content. Observed and multi-model mean is shown in black and red lines here, but you can see that the models have a large range for multiple scenarios of historic simulations. So this is a good example of how we look at historic simulations, just like what we did here. And finally, in terms of attribution, again looking at natural forcing, CMIP3, CMIP5 and observations, this total forcing does give us good representation of the observed trends. So models are reliable at a global mean sense of balancing energy and producing the observed trends. We don't expect them to produce year-to-year variability very accurately, but that's okay, and they are good for attribution. And the CMIP5 models have improved in many ways, as we know, but here what we are looking at is the trend observed, so trend with natural forcing only, which is what is called a counterfactual world. If human beings were not producing all these emissions, building cities and changing land, deforestation, agriculture and so on, what trend we would have expected? So mostly around zero, with few that are positive and negative. But observed trend over 1951 to 2010 is shown here, and this is the total natural and human forcing simulation from the models. And the main point I would make is that models are able to capture the polar amplification and the spatial variability of the warming in general. So as I said just a moment ago, CMIP5 models have gotten better at capturing some of the regional trends, which are very critical, because when we say 1.5 degrees C warming and 2 degrees C warming targets, they don't have much relevance for local changes. So models must be able to provide reliable information at local scales in terms of changes expected in the future for different scenarios, right? Otherwise they are not very useful. So model skill is improving in doing regional scale trends more accurately, at least in temperature. It still has issues with precipitation, but there are ways in which statistical properties of the past changes and trends can be used to constrain future projections, and there is a lot of work being done with that as well. Okay, so this gives us a confidence in at least creating what if scenarios for the future. So you can think of these as scenarios for the future, the range of changes we can expect based on the various activities or agreements and solutions we produce. So that allows us to choose different pathways to minimize impacts, or what they say typically as avoiding the unmanageable and managing the unavoidable. So that's the best we can do, and models are now becoming more and more useful tools for doing these things, and models will continue to improve and help with options for the future to avoid catastrophic pathways for ourselves, right, and for the other species that are on the planet and are facing some serious issues because of our activities.